Namaste to everyone. I welcome you all in my YouTube video channel. Today I will deliver lecture on theory of numbers, lecture number 21, in which I will discuss some theorems on congruence. Now we prove a theorem. Theorem is, let f denote a polynomial with integral coefficients. If a is congruent to b modulo m, then function of a means fa is congruent to fb modulo m. Now we prove this. Let we have a polynomial fx equal to c naught plus c1x plus c2 x square plus dot 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 plus cn x to the power n, where ci I equal to 0, 1, 2 dot 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 n belong to z, means integers. This is number 1. Therefore fa equal to c naught plus c1a plus c2 a square plus dot 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 plus cn a to the power n. This is number 2. And fb equal to c naught plus c1b plus c2 b square plus dot 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 plus cn b to the power n. This is number 3. Let a, b, c, d, m not equal to 0 are integers such that a congruent b modulo m and c congruent d modulo m. This is number 4 and this is number 5. From 4 and 5 we get AC congruent BD modulo M. This is number 6. And A plus C congruent B plus D modulo M from the properties of congruence. This is number 7. Let A equal to B equal to Cj and C equal to A to the power j, D equal to B to the power j. Therefore, from 6 we get here A equal to Cj C equal to A to the power j, congruent. B equal to Cj, D equal to B to the power j, modulo M. This is number 8. Using the concept of 7 in 8. In 7, we get if A congruent B modulo M and C congruent D modulo M, therefore their sum A plus C is congruent to B plus D modulo M. Therefore, we may use sigma in both sides of 8. We get j equal to 0 to n Cj A to the power j, congruent. Sigma j equal to 0 to n Cj B to the power j, modulo M, implies that here for j equal to 0, here we get C naught, here A to the power 0, 1. That means C naught, putting j equal to 1, C1 A to the power 1, means C1A plus C2 A square plus dot 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 plus Cn A to the power n, congruent. Now in right side, similarly C naught plus C1b plus C2b square plus dot 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 Cn b to the power n, modulo M. This is number 9. Using 2 and 3 in 9, we get FA congruent FB modulo M. Proved. Now we prove the next theorem. Theorem is AX congruent AY modulo M if and only if X congruent Y modulo M divided by GCD of A and M. Now we prove this. Prove. Let GCD of A and M equal to D, implies that we know A by D, M by D. GCD of A by D and M by D will be equal to 1. This is number 1. Given that AX congruent AY modulo M implies that M divides AX minus AY, implies that AX minus AY equal to some integer k multiply M, k is an integer, implies that A common X minus Y equal to k multiply M, implies that A by D X minus Y equal to k M by D, dividing D in both sides. Since D is the GCD, so D is not equal to 0. this implies that m by d divides a by d multiply x minus y. This is number 2. GCD of a by d and m by d is 1. Therefore, by Euclid's lemma, m by d divides x minus y. Since a by d, m by d, GCD of a by d and m by d equal to 1, implies that x is congruent to y modulo m by d, implies that x is congruent to y modulo m by d be the GCD of a and m. Proved. Conversely, let x is congruent to y modulo m by GCD of a and m, implies that m by GCD of a and m divides x minus y, implies that x minus y equal to, let k1 be an integer, m by GCD of a and m. k1 is an integer, implies that a multiply x minus y equal to k1 multiply a m by GCD of a and m. Let this is number 3. Since GCD of a and m divides a, implies that a equal to, let k2 be another integer, multiply GCD of a and m. This is number 4. Using 4 in theory, we get ax minus ay equal to k1, a means k2 GCD of a and m multiply m by GCD of a and m equal to k1 k2 multiply m. Since k1 and k2 be two integer, their product is another integer, implies that m divides ax minus ay, implies that ax congruent ay modulo m. Proved. Now we solve a problem. Problem is, if ax is congruent to ay modulo m and GCD of a and m equal to 1, then x is congruent to y modulo m. Now we solve this. Solution. We know that if ax is congruent to ay modulo m, then x is congruent to y modulo m by GCD of a and m. This is number 1. Given that GCD of a and m equal to 1, putting this value in 1, we get x is congruent to y modulo m divided by 1. That means x is congruent to y modulo m. Proved. Now we prove the next theorem. Theorem is x is congruent to y modulo mi. I equal to 1, 2, ... r. If and only if x is congruent to y modulo LCM of m1, m2, ... mr. Now we prove this. Firstly, we prove the necessary part. Given that x is congruent to y modulo mi, I equal to 1, 2, ... r, implies that mi divides x minus y. I equal to 1, 2, ... r. Here, if we put the value of I equal to 1, then m1 divides x minus y. m2, if we take value of I is 2, m2 divides x minus y. ... mr divides x minus y. Implies that x minus y is a common multiple of m1, m2, ... mr. But LCM of m1, m2, ... mr be the least common multiple of m1, m2, ... mr. Since least common multiple divides the common multiple, therefore least common multiple of m1, m2, ... mr divides x minus y. Implies that x is congruent to y modulo LCM of m1, m2, ... mr. Necessary part proved. That is n part proved. Now sufficient part. Let x is congruent to y modulo LCM of m1, m2, ... mr. Implies that LCM of m1, m2, mr divides x minus y. Let this is number 1. Since mi divides LCM of m1, m2 mr, I equal to 1, 2 r. This is number 2. Therefore, from 1 and 2, we get mi divides x minus y, because mi divides LCM of m1, m2, mr, and LCM of m1, m2 mr divides x minus y. That means mi divides x minus y, I equal to 1, 2 r, implies that x is congruent to y modulo mi, I equal to 1, 2 r. Therefore, sufficient part proved. Now we prove the next theorem. Theorem is a and b be integers, then a is congruent to b modulo m if and only if there is an integer k such that a equal to b plus km. Now we prove this. Given that a, b are integers such that a is congruent to b modulo m, implies that m divides a minus b, implies that a minus b equal to some integer k multiply m, implies that a equal to b plus km. Proved. Conversely, let a equal to b plus km implies that a minus b equal to k multiply m, implies that m divides a minus b, implies that a is congruent to b modulo m. Proved. Thanks for watching my video. If you are satisfied with my presentation and contents, then please click on like button and do subscribe my YouTube channel. Thank you.